You pour a driveway. 20 years later, it cracks. You build a seawall. A single storm can crumble it in a decade. But 2,000 years ago, someone mixed volcanic ash, lime, and seawater, poured it into wooden forms, and walked away. That structure is still standing today. Waves have hit it every single day since. It has not crumbled, it has gotten stronger. How is that possible? The real answer is far stranger than the Romans just built things better. For centuries, engineers assumed the fall of Rome meant the loss of a lost recipe, a secret formula, buried with the empire. But that's not quite what happened. The truth is not about a lost secret, it's about a chemical reaction we only recently learned to actually see. Picture the Bay of Naples. Sometime around the 1st century, Roman workers are hauling volcanic ash from the slopes near Pozzuoli. This ash has a name now, pozzolana. It's gray, gritty, and unremarkable to look at. But mixed with lime and seawater, it does something almost no other material on Earth does. It reacts, not once. Not just when it's poured, it keeps reacting for centuries every time salt water touches it. The Roman engineer Vitruvius wrote about this material in the 1st century BCE, describing how it hardened underwater in a way that baffled builders of his own time. He didn't understand the chemistry. Nobody did. Not for 2,000 years. He just knew it worked, and he wrote it down so other builders could copy it. Modern concrete is different. Your sidewalk is made mostly of Portland cement, which is chemically engineered to be dense and uniform. Dense and uniform sounds strong, but it's actually fragile in one specific way. When tiny cracks form, and they always do, water gets in. Steel rebar inside starts to rust. The rust expands, the concrete fractures from the inside out. Most modern concrete structures are engineered to last 50 to 100 years. Some fail in half that time. Roman concrete doesn't have that problem. Why? For decades, this question sat mostly unanswered. Then, in 2023, a team led by MIT materials scientist Admir Masik published a study that finally explained what was happening at a microscopic level. His team examined 2,000-year-old concrete samples from the ancient city of Privernum and found something previous researchers had overlooked entirely. Tiny white mineral deposits scattered throughout the concrete, called lime clasts. For years, those white specks were dismissed as a mixing error, sloppy Roman workmanship, bubbles the ancient builders failed to smooth out. They were not a mistake. They were the entire mechanism. Masik's team discovered that Romans were likely using a technique now called hot mixing. Instead of pre-slaking the lime, mixing it with water before adding it to the batch, Roman builders may have added quicklime directly, letting it react at extremely high temperatures inside the mixture itself. This created those small reactive lime clasts embedded throughout the concrete. Here's the part that changes everything. When a crack eventually forms in Roman concrete, water seeps in, just like it does in modern concrete. But instead of causing damage, that water reacts with the leftover lime clasts. The reaction produces calcium, which recrystallizes and fills the crack. Sometimes within weeks, the material heals itself. Your phone doesn't do that. Your car doesn't do that. Almost nothing humans have engineered does that except this 2,000-year-old formula, sitting quietly under the Mediterranean. Geologist Marie Jackson at the University of Utah spent years studying Roman harbor structures specifically for this reason. She examined breakwaters at sites like Portus Cassanis, concrete that has been submerged and battered by waves continuously since it was poured. What she found was almost the opposite of decay. In seawater over time, rare minerals form inside the concrete. One of them is a mineral called aluminous taubermorite, which barely exists anywhere else on the planet. Normally, concrete exposed to seawater falls apart faster, not slower. Saltwater is corrosive. It's why modern piers and jetties need constant, expensive maintenance. But Roman marine concrete gets tougher the longer it soaks. The seawater itself becomes part of the reaction, growing interlocking mineral crystals that make the structure denser over time. It's not resisting the ocean, it's absorbing it. Marine archaeologist John Olson, who has spent decades studying Roman harbor engineering across the Mediterranean, documented breakwaters and piers that have survived storms, earthquakes, and 2 millennia of tidal battering, structures that any modern engineer would expect to fail within a single human lifetime. So why don't we just use this today? It's not because we can't. It's because of trade-offs nobody talks about in a driveway commercial. Roman concrete cures slowly, sometimes over years, gradually gaining strength as those mineral reactions continue. Modern construction runs on speed. Skyscrapers need to be poured, cured, and load-bearing within days, not decades. There's also the matter of steel. Roman concrete wasn't reinforced with rebar the way modern concrete is because rebar didn't exist yet. Iron reacts badly with the chemistry that makes Roman concrete self-healing. Combine the two, and you often get the opposite of durability. So modern builders made a trade, speed and strength, in exchange for a shorter lifespan. It made sense for an industrial world building millions of structures at once. It just also means most of what gets built today is quietly designed to eventually need replacing. There's something oddly human buried in that trade-off. Ancient builders weren't in a hurry. They built for grandchildren they would never meet, for cities they assumed would outlast them by centuries. Modern infrastructure, by contrast, is often built for the next fiscal quarter, not because anyone chose decay on purpose, but because speed became the thing that got rewarded. Researchers today aren't trying to recreate Roman concrete exactly, they're trying to steal its logic. Self-healing concrete is now an active field, engineers embedding bacteria or capsules of healing agents into modern mixes, hoping to replicate what those ancient lime clasts did by accident, or maybe not by accident at all. Some archaeologists now believe the Romans understood more about this chemistry than we ever gave them credit for. Not through equations, through generations of trial, failure, and observation passed down as tradition. Think about that the next time you see a hairline crack spreading across a parking lot, or a bridge closed for emergency repairs decades before anyone expected. Somewhere in the Mediterranean, a slab of concrete poured before the printing press existed is still absorbing the tide, still getting stronger without a single person maintaining it. We didn't lose a secret formula. We traded it away piece by piece for speed. We didn't know we'd need this badly. So the next time you pour a driveway, remember, it won't crack in 20 years because the Romans forgot how to build. It will crack because somewhere along the way we decided that lasting a lifetime was good enough.